Now let's discuss the distribution of molecular speeds in a gas. This is a curve which was given by Maxwell. That's why it's known as Maxwellian distribution curve. This curve was actually plotted between a function and the speed of gas molecules. And this is a function which gives a relative number of molecules at a particular speed. Say at a particular speed v, within a range say from v to v plus dv, the number of molecules are given as say n or say dn. Say dn are the number of molecules which are having a speed within the range from v to v plus dv. And this function gives us the idea about the number of molecules, for which we can also write number of molecules which have speed and range from v to v plus dv are dn, and this dn can be given as fv dv. So you can say this function fv gives us the idea about the number of molecules per unit range of the speed at a particular speed v. So this dn number of molecules are there within the range dv. So we can write it as fv dv because fv is defined as the number of molecules per unit range of a speed. So dn can be given as simply fv dv. And here you can very easily calculate the total number of molecules by integrating this from 0 to infinity. As we know, in a gas there are few molecules which are moving at very slow speed and some are having quite high speed. So molecular speed is distributed within a very vast range from 0 to a very large value, which can be theoretically taken as infinity. Now in this situation, when we talk about the maximum number of molecules, that will be having the speed which can be written as the most probable speed, and slightly higher than this is the mean speed, which we can write as v mean. If we find out the average of this curve, it will be slightly lower than the most probable speed. And when we talk about the RMS speed, as just now we have taken in the previous article, that RMS speed is the least speed, which is the maximum speed which the particles are having, which is more than the mean speed and which is more than the most probable speed. Now in this situation, we can also find out the total number of molecules if we are having the distribution function. So here total number of molecules in a gas can be directly calculated as integration of fv dv from 0 to infinity. Practically no molecule is moving at a speed infinity, but to get the proper area below the curve, we can integrate it from 0 to infinity for the theoretically absolute value. Now in this situation, again we can write as fv is the number of molecules per unit range of a speed. We can define another function as here it is say fv upon n. That will be, you can simply state the function per unit range of a speed per molecule, or we can say per molecule the speed we can calculate it, and if we integrate it by multiplying with dv from 0 to infinity, this will give us unity, because from here also you can calculate several times this defined as another function f1 of v dv, which is integrated from 0 to infinity, which results just unity. That means it gives us a probability distribution function for all the molecules or for any molecule for a particular speed, always the probability for its speed within the range from 0 to infinity is always 1. In this way also you can analyze. And this function, when we talk about this Maxwell velocity distribution function, this can be calculated by using various statistical method. We can write Fv is obtained by statistical methods, and it is given as, again right now I'm not going into the derivation of function. You just keep this expression in your mind, although this expression will not be used much in any of the numerical analysis within your scope of your syllabi or the curriculum you are following. It is 4 pi nv square m upon 2 pi rt to power 3 by 2 multiplied by exponent e to power minus mv square upon 2 rt. And here all the symbols in these functions are having a standard meaning.